other 2 hour.
Good morning. So let's discuss in today's lecture more examples, or let's discuss some examples about RC circuit transients. So what's the transient? We already discussed this last lecture, which is something happened for a short period of time. And basically in circuit analysis, it is the charging or the discharging period for the inductor or the capacitor. Then last lecture, we start explaining the procedure in how to do the RC circuit transients. So basically in our analysis, we will assume there will be only single storage element. It can be either inductor or capacitor. And there are procedures for each one. So the first one in the RC circuit, which is including only a combination of resistors and only single capacitor, there are some procedures so we can avoid using the differential equation techniques, which is either time domain or Laplace transformation, which is in frequency domain. So how to deal with this? We already discussed this last lecture, which is we should assume the general solution is known. So Vc of t equal Vc of infinity minus Vc of infinity minus Vc of 0 e power negative t over tau. Then we have three unknowns. These three unknowns are Vc of infinity, Vc of 0, and tau. How to find them? We need to draw three different circuits. So Vc of 0, which is before the switching action. Before switching action. Then before switching action, we already are in steady states. Therefore, we will assume the capacitor is open circuit because we are in steady state. Then make the switch at the initial position because again, this is before the switching action. Then solve for the capacitor voltage. That's step number one. Step number two, change the status of which is after the switching action. You need to change the status of the capacitor of the switch. Then find R Thevenins across the capacitor terminals. Basically, in order to find R Thevenins, you need to turn off the sources, which is any voltage source will be short, any current source will be open. After that, tau will be R Thevenins times C. Then the last step to find the third unknown, which is Vc of infinity, which is at t equal infinity after a long time when the switching action occurred, which is we assume as t equal infinity, or in other words, c equal 5 tau. Then we can apply the new switch status. Here we are at steady state, therefore the capacitor will be open circuit as well. Then apply the new switch status and find the open circuit voltage. So you will realize voltage, or step 1 and step 3, are very similar to each other, but the only difference is the switch status, which is step number 1 when before the action, step number 3 after the action. That's the only difference, while step number 2, just calculate R Thevenins. But keep in mind, calculate R Thevenins across the capacitor terminals and apply the new switch status. Okay, here's an example. So I think when we do it with the examples, it will be much easier for us. So how do we solve this circuit? I forgot also to mention a formula. If here, this formula, we are using it to calculate the voltage. But if you need to calculate the currents, we will say the current is the time, which is C, the time derivative of the voltage. So you need to know both formula, this one and this one, 1 and 2. In case if you need to calculate the currents, you can use first find the voltage, then next find the current by applying the time derivative. And we know how to find the derivative of an exponential, which is the exponential itself times the constants. Now, solve for V of t, and I can add also I of t in this circuit, on this diagram. Look at this one. Now, how can we recognize, is this one transient circuit, which is in chapter 4, or is this one normal circuit like in DC in chapter 3 or 2? How can we distinguish? It's very important to look at, there is a switch. Since there is a switch, then definitely this problem is a transient. That's how we recognize. So it's very important. When you see it anywhere, like in exams or in the quizzes or everywhere in the book or when you see in the problems, you need to know this problem is a transient problem by looking at the switch. If there is a switch, then this problem is transient. If there is no switch, it's not transient, so you need to apply to make the capacitor open circuit, you made the inductor short circuit. So you need to keep this in mind, okay? Now, with this one, there's a switch, so it's transients. Then the second thing you need to look at to determine, is it RC or RL circuits? There are resistors, and look, there's capacitor. So it is RC circuit, and this should be only single capacitor. That's in this course. Then we have only single capacitor, and there is a switch, therefore it is RC circuits. In RC circuit, even if you need to find the currents, you need to find the voltage first. After that, you can calculate the currents. How? Apply the general formula, which is Vc of t equals Vc of infinity minus Vc of infinity minus Vc of 0 between brackets times e power negative t over tau. And if you need to calculate the current, we can say Ic of t equals c, the time derivative of the voltage. V sub c of t over d, which is, after calculating the voltage, then you can find the derivative to calculate the current. And you can see that we are using lower cases. Why? Because it is no longer DC, it's changing with time, it's function of time, therefore we are using lower cases as Ic of t, as Vc of t. While when we say Vc of infinity, it's constant, therefore Vc of infinity and Vc of 0 are upper cases because they are constant, they are not function of time. Or whatever, keep this in mind that when it's function of time, of t, we will make it lower cases. Okay, so what should I do? The first step, keep in mind to draw this, to write these two, Vc of t and Ic of t. That's the first step, so you can make your plan. So after writing this, my plan now is, we have 3 unknowns. So my plan is to find these 3 unknowns, then I will substitute everything here in this question. So I need to know Vc of infinity, Vc of 0, and tau. And we know tau, which is R Thevenin's times C. So we need to do 3 different circuits to find these 3 unknowns, or 3 steps. Okay? That's how I plan my answer. So it's very important to plan very well so you know what's going on. Now, let's start to do step by step. So the first step to do to find Vc of 0, second step to find tau, third step to find Vc of infinity. That's according to our procedure. So we have our procedures here, then we can apply it. So step number 1, when t less than 0. When t less than 0, apply the new switch or the initial switch status, and we are at steady state, therefore the capacitor will be open circuit. It's very important to make sure you understand these two. After that, draw the equivalent circuits. So here's the equivalent circuits. The initial switch status is closed. The initial capacitor status is open, right? That's what it's, because we are at steady state. The capacitor at steady state is open circuits, and the switch status is initially closed. So I'm gonna redraw the circuits and put the new, puts my modifications on it. So here the voltage source 20 volts remain the same. Here is the resistance, 5 ohms. 5 ohms remains the same. Here is the switch is closed. That's the initial switch status. Here is 2 ohms. Then there is a voltage source plus minus 50 volts. Then we have a resistor here, which is 15 ohms. Then here is the capacitor terminals. The capacitor will be open circuits. Why? We are at steady states. Our target is to calculate the voltage here, Vc of 0. Now, how can we calculate the voltage? Now, it's DC circuit analysis. You don't need to worry about the transients because now we convert this step number 1, this is now a DC circuit. How can I find Vc of 0? According to our procedure, the first thing is try to label the currents, right? So the currents, I'm going to start the current of the source going out from here. So the source current will keep flowing here. Now, do you think it will split? What do you think? No. Why?
Because the 50-volt source is stronger than the 20-volt source.
I'm talking about like the splitting at this node. Do you think the current will split? Why it will not split?
Because there's an open circuit.
Exactly, there's an open circuit. So the current needs a closed path. So we can say the current here equals 0. The current here remains as IS. So we have a single loop but with 2 voltage sources. So I cannot apply the single loop formula because we have 2 voltage sources. So what should I do to find IS? Any recommendation? What should I do? I need to calculate IS, the current here. I know the current of this one is equal to 0. I need to calculate this current. How can I calculate IS? It is single loop, but
voltage in a single loop.
Single loop formula cannot be applied. So basically, you can combine the voltages this one way. There is another way, do KVL. So again, to find the voltage, KVL. I think KVL will be much easier for us. So we can do KVL at this loop. I can call it loop 1. So KVL, loop 1. Start from the left bottom corner, then go clockwise. We need to determine the voltage polarities for the elements. So this is plus minus VR1. This is plus minus VR2. This is plus minus VR3. This is, I can call it VS1. This is SVS2. Now, start from the left bottom corner, which is here negative 20, or negative VS, let me write it as a symbol, negative VS1, then plus VR1, then plus VR2, then plus VS2 equals 0. Now substitute the values. It will be negative 20 plus VR, use Ohm's law, 5 times I source, plus 2 times I source, plus 50 equals 0. Therefore, I source will be 20 minus 50 over 5 plus 2. So the answer will be, of course, negative 4.29 amperes. That's I source. Okay. Now we just calculated I source. Then what else? Remember, our target is to calculate VC of 0. So VC of 0, where is it located? In the second loop, which is loop number 2. Now we can apply KVL at loop number 2. But you need to keep in mind that when you look at this resistor, or VR3, which is I times R3. I is 0 times R3, which will make it 0. Therefore, since it's open path, this resistor can be cancelled. Because the 0 current means 0 voltage, then cancel this resistor. Okay? Does this make sense? Now, we can do KVL in loop 2 to find VC of 0. KVL. Loop 2 or mesh 2, whatever. Start from the left bottom corner, negative VS2, then negative VR2, then we will hear plus VR3, plus VC of 0 equals to 0. Now substitute the values, VS, which is here negative 50, VR2, which is 2 times I times R. I, we calculated I source as negative 4.29 times R, which is 2, plus VR3, we already said it is 0, plus VC of 0 equals 0. Then the only unknown, which is VC of 0, then VC of 0 will be 41.43 volts. So we just calculate the first unknown. Okay? Is this clear? So remember that the 15 ohms resistor, since there is no current flowing to it, or the current is 0, therefore the voltage I times R, which is 0 times R, which will make it 0. Just like all this. Yes?
How come there's a voltage change across VC if there's no current flowing over there?
Where?
Like, how are we able to calculate a voltage change across VC?
Yes.
That whole loop doesn't have any current.
Yes, so even if there's open path, but there's still the voltage, that's fine. It does not mean open path, there is no current. For example, the wall, like, link a multimeter, you will read a voltage, but there is no current. Okay, any question? Okay, now we are done with the first step. Let's go to the next one. So the next one is to calculate tau. to calculate tau, which is R Thevenin's times C. How to calculate tau? Let's go back at the circuits. Apply the new switch status. This is very important. Don't forget to apply the new switch status. The switch status initially is closed, then it will be open. So make it open. After that, find R Thevenin's across the capacitor terminals. In calculating R Thevenin's, you need to turn off the sources. Any voltage source will be short, any current source will be open. Now, how many voltage sources, how many sources do we have? We have two. We have 20 and 50 volts. They are all will be short circuit because they are all voltage sources. So let's redraw the circuits. By making all of the sources, voltage sources as short circuits, any current source as open circuits, apply the initial switch or the new switch status, find R Thevenin's across the capacitor terminals. So it's very important to draw the circuit correctly, then you can guarantee everything's fine. So the 20 volts voltage source will be short circuits because it's voltage source. Now the 5 ohms remains. The new switch status is open. 2 ohms resistor remains. 50 volts voltage source short circuits. Then 15 ohms here. Then we need to calculate, here is the capacitor terminals, we need to calculate R Thevenin's here. How to calculate R Thevenin's into the circuits. So drawing the circuits is 70% of the answer. So you need to make sure that you're drawing it in the right way. Now, keep in mind the 15 ohms resistor remains. Why? This step number 2 different than step number 1. Step number 1, we said it's open circuits because there is no current flowing. While step number 2, or try to treat each step as independent. So if we neglect the 15 ohms in step number 1, this does not mean we will neglect it in step number 2. So that's one of the common mistakes or the fatal mistakes that I used to see many students fail on it. Because some of them, they said, okay, the 15 ohms resistor has already been cancelled in step number 1, then I'm going to cancel it here. Don't cancel it here. Consider each step as a standalone or as different questions. Okay? They are all independent of each other. Now, how to calculate R Thevenin's? Remember, we need to calculate R Thevenin's across the capacitor terminals. I can say A and B. Now, you need to assume a current going from A to B, or you can first label the nodes. There is a node here. There is a node here. A node here. Then a node here. Now look at the 15 ohms and 5 ohms. 15 and 5. Are those in series or parallel? They are common in one node, not 2 nodes, then they are not parallel. Now, the other thing, are those sharing the same currents? What do you think? Let's assume there is a current going from A toward B, A to B. Do you think the current will go here? No, it will not. So, why it's not? Because it's open path. So I need to go from A to B. That's the only path that I can go. So we can say 15 and 5 are in series because they are sharing the same currents. Do you think the 2 ohms, is there any path to go from A to B by passing 2 ohms? No. Therefore, the 2 ohms will not be included in R Thevenin's. So R Thevenin's will be 15 in series with 5, so it will be 20 ohms. Okay? Does this make sense? Yes.
So how can you just cancel out 2 ohms again?
Okay, is there any path to go from A to B through the 2 ohms resistor? You need to have, I'm going from A, or through the 2 ohms resistor, I cannot continue to B. Or let me go from B through 2 ohms, I cannot continue. That's why there is no way to go from A to B through the 2 ohms resistor, then therefore they are, it's not counted. Then R Thevenin is equal to 20 ohms. So remember, our target is to calculate tau, which is R Thevenin's times C. Then it will be 20 C is given in the question as 0.1 farad. So the answer will be 2, and it's actually 2 seconds. The unit of the tau is seconds. Then, now we are done with the second step, which is calculating the second unknown. Then we still have the third step. Step number 3, to calculate VC of infinity, which is at t equal infinity, or in other words, 5 tau. Tau is 2 seconds, which is at 2 equal 10 seconds. So here in this example, we have defined the infinity as 10 seconds. Okay, now what should I do? Redraw the circuits. Now, at t equal infinity or 10 seconds, we are at steady state. So make sure to put the capacitor as steady state, or replace the capacitor by open circuits. Apply the new switch status. That's also something important. So I'm going to redraw the circuits. It's very important when you do for each step, draw equivalent circuits. Don't solve them for only one circuit. Draw equivalent circuit for step 1, or draw a circuit for step 1. Draw a circuit for step 2, draw a circuit for step 3. Because again, each step is independent of each other. Now the simplification that we did in step number 1 does not mean we will apply it in step number 2, does not mean we will apply it in step number 3. So what should I do? Look at the circuits. I'm going to replace the capacitor by open circuits, apply the new switch status, which is open. That's what I'm going to do. So let me redraw it. So here's plus minus 20 volts, 5 ohms. Then the switch status, new switch status, which is open. Then here is 2 ohms resistor, 2 ohms. Yes. Then 50 volts. Then 15 ohms. Then what else? Plus minus VC of infinity. That's what we need to do. So we need to calculate VC of infinity. How to calculate this? Again, try to find the currents. That's our procedure. It's like a DC problem analysis. So let's assume there is a current going here, like as a source. Do you think the current will split? No, it's open path. So how can we calculate the currents? Do you think actually there will be a current? The current needs a closed path. Is there any closed path in the circuits? Where is it?
VC is the source. And then the closed path goes from the positive terminal AC around the outside loop to the negative terminal.
Yes, but now as a DC circuit, we will assume the capacitor is open circuit. So now it's open circuits. So is there any path to the current to flow, for the current to flow? No. This means there is no currents at all, right? So the currents are zeros. So I equals 0. There is no current here, even here. I equals 0. Here I equals 0. There is no currents because, again, there is no possibility to make any closed path. No closed path for the current to flow. So as a result, what do you think the voltages of the resistors will be? Zeros. So here V equal I times R, which is 0. Then V equal I times R, which is 0. V equal I times R, which is 0, right? All of the voltages are zeros. So we can simplify this circuit like this one after the simplification. So here's 20 volts plus minus 50 volts plus minus VC of infinity. That's the circuit after simplification. Because there's no currents, all of the resistors will be zeros. The voltage of these resistors will be zeros. Then if the voltage is 0, current is 0, erase these elements. Now, with this one, how can I calculate VC of infinity? Can I do KVL here? Yes, but there is unknown of this voltage. I'm going to call it Vx. Vx is unknown. So I don't think it's a good idea to apply KVL here. I can do KVL, this one, to find Vx. Then I can do another KVL here to calculate VC of 0. But this will take a lot of time. I mean, why do we need to do this? How about doing KVL at the outer loop? Yes, there will be one unknown, right? Look for a KVL such that there's only one unknown. That's one way. There is another way, which is look at V source or VC of infinity at the positive and the negative. So we will see that VC of infinity and the 20 volt source are in parallel because they are common in two nodes. And parallel means sharing the same voltage, right? So as a result, we can say VC of infinity equals 20 volts. If you don't want to use this, or if you like average, like sometimes you might not get this idea, so just do KVL, such that there is only one unknown. So VC of infinity equals 20 volts. Now the third unknown done. Okay? Now we just calculated the three unknowns. Remember, we are not done yet, so make sure to continue. Don't say don't stop here. You need to go back and substitute them because your target is not to calculate the three unknowns alone. Your target is to calculate VC of t and to calculate IC of t. And what we did here is just calculating the three unknowns. Yes?
Can you explain how you got the 20 volts one more time?
Here?
Yes.
Okay. So you can either do KVL at the outer loop, or when I label the nodes, you see like VC of infinity and 20 volts source between the pink node and the blue node. Therefore, these two are in parallel. And parallel means sharing the same voltage. Then those voltages are the same. In other words, you can do KVL and you will see. You can do KVL, it will be negative 20 plus VC of infinity equals 0. Therefore, VC of infinity will be 20. This is another way. Just by do KVL at the outer loop. Okay, any other question? Okay. Now, after calculating the three unknowns, go back to the general solution. The general solution which is VC of t equals to VC of infinity minus VC of infinity between brackets minus VC of 0 e power negative t over tau. Now substitute the values. VC of infinity is 20. VC of 0 we calculated it as 41.43 e power negative t over tau, which is 2. That's the expression. Now simplify it more. After doing simplification, 20 plus 21.43 e power negative 0.5 t. And the unit, of course, is volts. That's VC of t. And remember, our target is not only to calculate VC of t, also in this question you are required to calculate IC. So IC of t will be C, the time derivative dV by dt, which is 0.1. The time derivative of 20 plus 21.43 e power negative 0.5 t. Now, how to calculate this? You know how to apply the derivative, so I'm gonna draw it. Oh, okay, no space. Okay, I can write it here. So IC of t will be 0.1 times 21.43 times negative 0.5 e power negative 0.5 t. Then you can calculate this. Actually, I don't have the exact number, but you can calculate it for calculating IC of t. Basically, you need to calculate 0.1. I can simplify it in another way, which is negative 21.43. It will be like this. Let me fix it. Negative 2.143 over 2 e power negative 0.5 t amperes. That's IC. Okay? Any question about this example? So that's that's it. That's how we can solve the circuits, like IC circuits, RC circuit, by doing like first write the general solution. Then we have three unknowns, three different circuits. Then back substitute these three unknowns. Then find the derivative to find the currents. So this example with RC circuit transit, it's cumulative. So we are doing Thevenin's, we are doing KVL, KCL, Ohm's law. Maybe you can do source transformation, voltage division, current division, whatever. There are multiple ways. Then after that, it will be like transient. So the difficulty of this part, which is in being cumulative. Okay. Again, any question? Now let's go to the second example. Solve for Vt for t larger than 0. We need to calculate the voltage of the capacitor. So you need to locate where is Vt here. And is this one transient problem, yes or no? Look at the capacitor, look at the switch, yes, it's transient problem. How to do this? And I can add and solve for I of t, which is the currents of the capacitor. So the first step, you need to write a general solution, which is, I'm going to write it here, Vc of t equals Vc of infinity minus, between brackets, Vc of infinity minus Vc of 0, e power negative t over tau. To calculate the current, I sub c, all of them, when you see c here, I mean sub c. Okay, Ic of t equals to c, the time derivative, Vc of t by dt. Now, we have three unknowns. These are Vc of 0, tau, Vc of infinity. Therefore, there should be three steps. Step number 1, when t less than 0, which is before the switching action, we are at steady states. So the capacitor will be open circuit, apply the initial switch status. So steady state, I can write it as SS, and initial switch. So I'm going to redraw the circuits. Here is 18 volts. Here is 3 kilo ohms. Here is the capacitor now is open circuits. Because we steady state, we need to calculate Vc of 0 like this. Then here is the 6 kilo ohms, the initial switch status, which is open. Then here is the 3 kilo ohms. Here is plus minus 6 volts. And we need to calculate Vc of 0. So by looking at this circuit, we can say that, let's label the currents. Here is I source. Do you think the current will split? No, because the current requires closed path. So here I equals 0. Here it is continue as I source. Do you think the current will split here as well? No, because it is open path. So the current needs a closed path. Therefore, we realize that all of this loop sharing the same currents. So how can I calculate the currents? There is one way by finding the equivalent voltage sources, the equivalent resistance. So it will be as one single voltage source, single resistor. Or there is another way by doing KVL. So let's do KVL. This can be as plus minus V1, plus minus V2, plus minus V1, plus minus V2, plus minus V3. Now this is VS1, this is VS2. So I can do KVL at the outer loop to calculate the currents. KVL, outer loop. Start from the left bottom corner and we'll go clockwise, like this. Then it is negative 18, or negative, let me write it as a symbol, negative VS1 plus V1 plus V2 plus V3 plus VS2 equals 0. Now you should be more professional in this, so we don't need to over-explain everything. I assume now we are all aware how to do KVL. We are all aware why we choose the outer loop. because we need to make sure to find the current such that there is only one unknown. Then substitute the values. So Vs is negative 18, I1 which is 3k times I source, V2 which is 6k times I source, V3 which is 3k times I source, Vs which is 6 volts equals to 0. Therefore, I source will be 18 minus 6 over 3k plus 6k plus 3k. So I source will be 1 milliampere, and milli because there's k, which is 10 power 3, 1 over k, 10 power negative 3, which is milli. Now, after calculating I source, we need to calculate VC of 0. How to calculate VC of 0? VC of 0 is located here. How to calculate this? You can apply KVL. Where KVL? Where should I apply it? It's up to you. You can apply KVL at this loop or at this loop. So for me, I prefer like this loop because it's easier analysis. So we can do KVL loop 1, then start from the left bottom corner, negative Vs1 plus V1 plus Vc of 0 equals to 0. Now substitute the values. It will be negative 18 plus I times R, which is 3k times 1 milli plus Vc of 0. Milli will k will cancel each other. Therefore, Vc of 0 will be 18 minus 3, which is in other words 15 volts. Okay? Is this clear? Now, for step number 2, which is we need to calculate to find tau. I think to make it easy, I'm going to make step number 2 here. Step number 2, to calculate tau, which is R Thevenin times C. Apply the new switch status. Don't forget new switch status. Then turn off the sources. Yes.
So in every step, you treat the capacitor as an open circuit.
Yes, you can say like this, right? But in step like 2, finding R Thevenins, we are not treating the capacitor as open circuit. We are calculating R Thevenins across the capacitor terminals, which is very similar to open circuit, yes. But I mean, technically, we cannot say open circuits. But it is treated as open circuit like this way because we are removing this device and calculating R Thevenins across it. Okay. Now let's apply the new switch status, turn off the sources. So the 15 or the 18 volts will be short circuits. That source, 18 volt, will be short circuits. And this source will be short circuit as well. So now I'm going to draw it here. 3 kilo ohms. Then here is the capacitor terminals. We need to calculate R Thevenins. 6 kilo ohms remains. The switch status will be closed. Then we have, remember that switch will be closed. That's why we make it like this way. Then 3 kilo ohms here remains. The 6 volts will be short circuit because it's voltage source. So we need to calculate R Thevenin. The best way is to label the nodes. Let's label the nodes. This is the same node. And there is another node here. And let's assume this is we need to calculate R Thevenin across it. Like this. 3 kilo ohms, 6 kilo ohms, 2 kilo ohms. Okay. Now look at the 3 kilo ohms in the right. It's both sides the same node, right? So it's shorted. Then the only resistors remaining, which is 3 kilo ohms and 6 kilo ohms. What's the relationship between them? Are those series or parallel? What do you think? Parallel. Why? Between the same two nodes. Why they are not series? They are not sharing the same currents. Assume there's a current flowing from A to B, it will split. That's why they are not sharing the same current. Then 3 kilo and 6 kilo are in parallel. So our Thevenins will be 3K parallel with 6K, which is 3 times 6 over 3 plus 6. So the answer will be 2 kilo ohms. And don't forget the kilo, the K kilo ohms. Now our target is not only to calculate our Thevenin, to calculate capacitance or tau. Tau, which is our Thevenin times C, which is 2 kilo times C, which is C is given as 200 microfarad. 200 times 10 power negative 6. Micro negative power 6. You need to be familiar with this, as written as mu f. Micro 10 power negative 6. So kilo 10 power 3. Then 10 power 3, 10 power negative 6. There will be some shortcuts, so the answer tau will be 0.4 seconds. So now we just calculated the second unknown. We already know. Now we know two unknowns. Okay, is this clear? The next step to calculate t equal infinity, t equal infinity, or in other words 5 tau, which is 5 times 0.4, 4 times 520, which is at 2 seconds. So here we have defined the infinity as 2 seconds. What should I do? Redraw the circuits, but apply the new switch status. So here is the circuit, the new switch status, which will be open. And make the capacitor open circuit because we are at steady states. So I'm going to redraw the circuits. Here is plus minus 18 volts. Here is 3 kilo ohms. Then here is plus minus VC of infinity. Then here is the 6 kilo ohms. The new switch status, which will be closed. Then here is 3 kilo ohms. Here is 6 volts. Now the next step is to currents. Label the currents. Here is I1. Here is I2. So I will keep going here, I1. Then it will go here, I2 will go here. Our target is to calculate VC of infinity. So let's calculate I1 first. And let me also label the voltages. Let me label the voltages first. Plus minus V1, plus minus V2, plus minus V3. And here is VS1, here is VS2. Now, let's do KVL at this loop. I can call it loop 1. KVL, loop 1. Start from the left bottom corner, negative VS plus V1 plus V2 equals 0. Negative VS, which is negative 18, plus 3K times I1 plus 6K times I1 equals 0. Therefore, I1 will be 18 over 3K plus 6K, which is 18 over 9. Then it will be 2, but there's K, so it will be 2 milliamperes. Now, the next step, since we need to calculate VC of infinity, we can do KVL at this loop too. So let's do another KVL at this loop too. Then KVL loop 2, it will be negative VS1 plus V1 plus VC of infinity equals to 0. then it's going to be negative 18 plus 3k times 2 milli plus Vc of infinity equals 0. Then we have only Vc of infinity, so Vc of infinity will be 12 volts. Okay? Now remember, we are not done yet, so our target is to calculate the expression, the voltages and the currents. So we just calculated the three unknowns. Now let's go and substitute them. I'm gonna substitute them here. I'm sorry for the messy, but I need to have a space. Now Vc of t. Uh-oh. Vc of t equal Vc of infinity minus Vc of infinity minus Vc of 0 e power negative t over tau. E power negative t over tau. Now substitute the values. Vc of infinity, which is 12, and Vc of 0 we calculated it as 15. So here is 12 minus 15 e power negative t over 0.4. So after doing some simplification, it will be 12 plus 3 e power negative 1 over 4, I think 0.25, 25t volts. That's Vc of t. Now, in order to calculate Ic of t, so that's Vc of t, and we are done with Vc of t. Let's to calculate Ic of t, which is C dV by dt, which is 200 micro, 200 times 10 power negative 6. Then the time derivative of this expression. Let's do the derivative. It will be 200 times 10 power negative 6. The derivative of 12 is 0. The derivative of the exponential, let's put the constant here, then negative 0.25, then e power negative 0.25t. Then it's going to be, you can calculate it. It will be negative, a number, e power negative 0.25t. And the unit, of course, ampere. You can use the calculator. Yes.
I think it would be, the exponent in Vc of t would be 2.5, right?
Let's see, 1 over 0.4.
Because when you divide by a number less than 1, then you're actually multiplying by a number greater than 1.
So 1 over 0.4, is it really 0.25?
2.5.
2.5, okay, that's, thank you. 2.5. Okay, so it's over here. 2.5, 2.5, and here 2.5. Okay, is this clear? Okay, we are not done yet. We still have 2 minutes. So, remember to go to worksheets number 6. So worksheet number 6 summarizes the procedure. Like we already discussed, and the procedure or how to solve this circuit has already been written, so I encourage you to practice this. So use, do it by yourself, try to practice. So don't look at the answers, try to solve it by yourself. Then after that, go back and compare your answers with the existing answer. Then you should get it. Then the next lecture, we will discuss the RL transient, which is very similar to RC, but with some changes. It's almost, there should be 3 unknowns, and we'll solve for 3 unknowns. Very similar way, but there are slight changes. And as you know, there will be a quiz on Friday, which is next lecture. That quiz will be on transient circuit, which is RC circuits. So if you know these 2 examples and the example in the worksheets, this should be more than enough to understand. And you are allowed to have a small note card for that quiz. So you can write whatever you want. A small note card, 3 by 5.
Okay.
Okay, so see you in
Introduce
right.